So thanks for the great introduction. We'll get started right away. And so I guess like Marco just mentioned, I think this talk will not be about drones specifically, but I think it would be kind of surprising to many of you if drones weren't kind of part of the talk in one way or another. So I'd just like to point out that basically drones are what I think kind of one of the first successful deployment of robotic system in unstructured environment that we have right now today operating in the wild and that can perform kind of autonomous tasks, like useful tasks, like for example, follow me video and these sorts of things. So really I see kind of drones as really kind of our first stepping stone as a community into kind of the real world with some kind of, with having robots operating in unstructured environments. If we looked at kind of where they have been successful so far and kind of zoom in on the application specifically where they've worked, there's something that kind of stands out. So if we look at them, for example, filming and photography, inspection and maintenance, mapping and surveying, something that is in common in kind of all these types of application is that they are applications where the agents, where the drone is very much acting as a passive observer, is very much acting as sort of a not really interacting with the environment, but really as an observer. And I would say that there's basically the defining factor really of kind of this generation of robotic system is that in general, that's kind of what their role are. And I would also add that kind of the key enabling technology for this is really kind of obstacle avoidance, for example, is a big one. So with that in mind, I kind of want to point to kind of, okay, so why is this, why do I think this is kind of the defining factor of what we can do today? Is that essentially, well, it's also what I think is where the limit is in terms of what we can do. So something that remains difficult for all these robots that we've deployed in the environment is that things like interacting with the environment, making and breaking contact, more specifically with the environment, remains extremely difficult. So for example, this work that I've been doing in haptics in collaboration with another group has been kind of very difficult to get working in practice and often requires us to get a lot of kind of ad hoc solution for specifically for the aspect of contact, of making contact between the drone and kind of the user. So in that case, we had drones interact with users that were interacting with it in VR and just kind of a lot of these interactions where the user was interacting with the drone, again, had to be kind of very ad hoc. So this allowed me to, I think, define what I think is going to be kind of the next generation really of robotic systems, kind of what our next big stepping stone is going to have to be. We're going to have to essentially bring our robots in a place where making and breaking contact with the environment is as easy as doing obstacle avoidance. So really kind of keeping track of the fact that, obstacle avoidance was kind of the first big enabling technology to get us this first generation of robots that are very much acting as observer in the wild. And now to get kind of robots that can do more, we're going to have to get them to be able to make and break contact with the wild. And so now it becomes the questions of how do we make that happen, right? What's going to be the key enabling technology to make and break contact in the environment? So with that question in mind, kind of at the beginning of my PhD, started to think and reflect on kind of our field and kind of think of where the breakthroughs really kind of came through in the last couple of years, specifically in controls. And I think there's something that is kind of stand out, is that a lot of the breakthroughs in controls actually come from breakthroughs in numerical optimization. So I'll make this a little bit more concrete. So for example, sum of squares problems, as an example, where once we've kind of figured out that we can solve this class of numerical optimization problem by solving semidefinite programs, which happened in the last couple of years, that kind of opened up a whole generation of obstacle avoidance algorithm that kind of gave us some very impressive results, including some of my own work, for example, doing mostly, again, obstacle avoidance. So really that's kind of what seems to be kind of a common story is that we get this kind of great progress in numerical optimization, and then this great progress in numerical optimization kind of really quickly translates to a huge step forward in control, in robotic control specifically. And so there's a simple question, right? In the context of now this Autonomy 1.0, where again, we're very much observing the environment, to Autonomy 2.0, where our agents are making and breaking contact in the environment, and knowing now that numerical optimization has very much been at the forefront of enabling kind of previous success in robotics, is now it becomes a question of, okay, is there currently progress in numerical optimization that could enable these sorts of interaction, this contact, right? It's kind of a natural question to ask. And as you might suspect, given the title of the talk, I believe that's the case. And I think a lot of progress that we've made in this specific class of problem called bilevel optimization problem is potentially the answer to that. So bilevel optimization problem are a very, very broad class of problem, but roughly speaking, what they are is when we have two optimization problems nested one into the other. So we either have a problem that appears in the constraint or in the objective of another problem. And throughout this talk, I will be talking about I will be referring to the embedded problem as the lower problem, and I will be referring as the kind of resulting problem as the upper problem. So we have this lower problem and this upper problem, and their combination is a bilevel optimization problem, which is, again, a nested optimization problem. This is a quick outline of the talk. So we're going through, with this introduction, we're going to go through part one, where we're going to talk a little bit about solution methods for these class of problems, including our own contribution in that area. And then we're going to talk about we're going to go more applied, and we're going to talk about problems in control that have this bilevel structure and that we've tackled with kind of modern advances in bilevel optimization. I want to specifically highlight our contribution just kind of to get us started and kind of make them more clear as we go along. But the first contribution that we've done is a general purpose solution method for bilevel optimization problem. Specifically, we've tailored it to robotics application. We've also demonstrated an efficient through contact trajectory optimization method that is based on bilevel optimization. We've also demonstrated an efficient value function learning method that is, again, as you might expect, based on bilevel optimization. And then we've also demonstrated a Lyapunov synthesis method. And these are the associated publications, which are all either on the press, except for the last one, which was submitted last week. And so we'll get started. So kind of getting into the meat of it, and hopefully this will be interesting. So let's talk a little bit about solution methods first. So the first thing I want to clarify to kind of not lose anyone is that I will be talking throughout this talk about getting the gradient of the lower problem. So getting the gradient of the embedded problem in bilevel optimization. And I want to clarify what I mean by that because it's easy to confuse. What I mean by that is I mean the gradient of the lower problem solution with respect to the lower problem's parameter. And that's really what I mean by gradient of the lower problem. And that needs to be contrasted with, for example, the gradient of the lower problem's objective or the gradient of the lower problem's constraints. So that's not what I'm going to be talking about when I say the gradient of the lower problem is, again, not a trivial gradient to get in general, is the gradient of the optimal solution of the lower problem with respect to its parameter. And often the parameter of the lower problem are going to be the decision variable of the upper problem. So we're also going to restrict ourselves to kind of a subclass of, we're going to restrict ourselves to a subclass of problems, where essentially the lower problem is differentiable. And we're also going to restrict ourselves to a subclass of solution methods where essentially that can be summarized essentially nesting two solvers one into the other. So from a high level, what essentially we're going to do to solve these problems is we're going to take a solver, we're going to solve the lower problem, the embedded problem, and then we're going to somehow differentiate the solution that was returned by the embedded solver. And then we're going to pass that to another gradient-based solver that's going to be solving the upper problem. So again, we're going to have a gradient-based nonlinear optimization solver that's going to solve the upper problem, and then we're going to have an embedded solver that's going to solve the embedded problem. And so given kind of that restriction in terms of class of problem and solution methods, we can divide essentially our way of solving these bilevel optimization problem specifically by how we're going to get the gradients of the lower problem. And it's not necessarily like a division that is found everywhere. I think that's just more me just trying to organize a little bit this into a way that I think ties in a lot of different work that you may have seen around and hopefully kind of contextualize a lot of them into this bilevel optimization framework. So the first way of getting the gradient of the lower problem is we're going to rely on properties of the solution. So we're going to call these fixed point based methods. And you can think of them as essentially being sensitivity analysis based. And what they do is they rely on properties of the lower problem. And then the second method we're going to have is to roll out the solver. So they're not going to rely on property of the solution, but they're instead going to rely on properties of the solution method of the lower problem. So it's kind of a not necessarily obvious distinction, but we're going to go through kind of really what that means in practice. So one of them is going to essentially differentiate the solution process of the lower problem, and the other one is going to use a property of the solution of the lower problem. I'm going to give you some example of kind of these two classes of solution methods, or at least work that I think is very well known out there, and that you know could be classified in one or the other. So for in terms of problems that use kind of this fixed point based differentiation. Sorry, this includes, for example, OpNet or neural IDs that, for example, solve embedded quadratic. So for OpNet, for example, solve for example, quadratic programs embedded into neural networks, and those use fixed point based methods. And then in terms of rolling out the solver, a lot of the meta learning approaches, for example, some of ASL's work uses more of kind of this rolling out the solver method. And obviously there's pros and cons into kind of the two different classes of approach. So if we're using these kind of fixed point based methods, the advantage of using that is that essentially the gradients that we're going to be looking for are actually only going to be dependent on the solution and not the solution method. Some of the cons, though, will be that this solution will not have to have certain properties, like, for example, it'll have to be an optimal solution of the embedded problem. Well, in terms of rolling out the solver, they'll be kind of more straightforward to implement in general. They can, for a simple problem, they can actually allow kind of very straightforward solution. And then, but it can also be sometimes for kind of harder problem, they can be much slower. So there's kind of pros and cons in both approaches, and they're kind of both, but they're kind of both useful in different settings. So that's why they're worth, I think, studying both. It's kind of going back at the two division. I'm just going to go through a little bit, explaining a little bit how both of these types of methods work. So first, focusing on the fixed point based methods, I'm going to walk you through the math, and I think this is not specifically how everyone is doing kind of fixed point based differentiation, but it's certainly the flavor of it. And I hope that's something you can kind of walk away with as having kind of demystified how neural IDs and OpNet, these sorts of things work that use this fixed point based differentiation. And so what we have, for example, is we're starting with our problem right on the left here, which is the lower problem, the embedded problem that has an objective and some constraint. That problem will have some primal variables, some dual variables, and some parameters, right? And what we're going to be looking for, as explained earlier, is we're going to be looking for the gradient of the lower problem solution with respect to the lower problem's parameters. So this is what we're looking for. And this is kind of our problem setup. What we're also going to define here is we're going to define our first order optimality condition, which are our KKT condition, right? That many of you know, that we're going to just write as this equality constraint here, this function g that has to be equal to 0, which essentially just is our first order optimality condition, our KKT condition for that problem. And we're going to make a simple observation, which is really at the core of these kind of fixed point based differentiation method, is that this KKT condition, so this first order optimality condition, has to hold for any parameters of the embedded problem, right? So if you give me any parameter z for the embedded problem, then the KKT conditions have to hold at the optimal solution, so x star and lambda star. So what that means, right, with that observation is that if you take the partial of the KKT condition of the lower problem, the partial has to be equal to 0, right? So if we change the parameters of the lower problem a little bit, the KKT condition always have to be equal to 0. So we have this equality constraint. Now, just a little bit of basic algebra. Now, if you just do the chain rule on this equality constraint, and then you literally just solve for the second term of that middle equation, you'll get essentially the term that we needed initially. So really, that the intuition behind these methods, again, is we start from our lower problem. We've taken our KKT conditions, which are a condition that any solution of the lower problem has to satisfy. And then with just a straightforward application of the chain rule, we essentially get the gradient that we need. So that kind of explains the fixed point based method. I'm going to talk a little bit about the other type of method, which essentially use automatic differentiation through the solution process of the lower solver, as opposed to looking at the solution of the lower problem. And specifically, we're going to look at, there's many different ways of doing that, and we're not going to cover all of them, but we're going to look at our specific contribution in kind of that area of solution method, which is what I'll present right now. So essentially what we decided to do is to see if we could solve these these Bilevel optimization problem by taking an off-the-shelf constraint nonlinear optimization solver. So in this case, SNOP is the one that we used in that particular instance, and then write a general purpose constraint nonlinear optimization solver that we could still keep differentiable to solve the lower problem. So a lot of the examples that I showed earlier, right, when we were talking about this class of solution method for Bilevel problem, a lot of times the upper problem was kind of this unconstrained problem, and people were using or then use gradient descent. In our case, we're going to use a constraint solver for the upper problem. So that's a big difference from what a lot of folks have done. And then we're going to write a custom solver for the embedded problem. Now, it's obviously not as easy as it sounds. Writing the solver for the embedded problem needs to have a lot of properties. For example, it needs to be robust, it needs to be fast, it needs to be differentiable, and it needs to be correct. So it needs to give us the right solution, but at the same time, it needs to be differentiable. So we need to be able to, essentially every step that it takes, we need to be able to run automatic differentiation through. So I'm just going to give you a super high level overview of that solver, but just to give you a sense of more or less how it works. So first thing we're going to do is we're going to convert our inequality constraints to equality constraints using shape softmax function. Shape softmax function. Then we're going to formulate our augmented Lagrangian, which essentially gives us the advantage that it's a slightly more smooth objective than the usual kind of Lagrangian. It's really kind of the property more or less that we're exploiting, making the solver, the kind of embedded solver, a little bit more robust. Then we're going to use method of multiplier for the first couple of steps, and then we're going to use roughly SQP after that for a couple of steps. And so unless you're kind of familiar with numerical optimization, a lot of this kind of might sound like we're kind of using a lot of kind of different method and combining them, and that's exactly what we're doing. We took kind of a lot of tricks that are well known in nonlinear optimization, and we kind of carefully chose the right ones to keep the solver both correct and fast, but also differentiable. So it's really just kind of like kind of building the right recipe, right, of numerical optimization method, and then using the right tools, in our case, Julia and automatic differentiation. But really what I want to stress is that even though it's sort of straightforward to come up with it, it's a very flexible approach now that we have kind of this solver, right? So again, what we now have is this nonlinear optimization solver, SQP, and then this custom differentiable solver that we can put together with SNOP and then solve all sorts of problems. So for example, we have just as an example, a simple robust control problem where we'll have the upper problem is going to be some trajectory optimization problem. And the embedded problem is going to be a worst disturbance, right? So what we're going to be trying to do is, for example, move an arm from an initial position to a last position. And the arm is, for example, in that case, mounted with a plate, and the external disturbance is some wind that is modeled as you know, having potentially more effect horizontally, as usually wind works. Than vertically. And so what the optimization problem is going to try to do is to come up with a trajectory such that the worst case win is minimized. And really what I want to stress with this example is not necessarily that specific example as much as the fact that this problem formulation is kind of very flexible and allows us to put that worst case disturbance in either the objective of that problem or in the constraint of that problem and get kind of pretty different solution depending on what we want. And so for example, if you put that worst case disturbance in the objective of your trajectory optimization, you'll get a trajectory that will, you know, try to minimize the worst case disturbance kind of evenly across the trajectory, but you can also constrain that worst case disturbance to never exceed some amount over some like period of time. So depending on which case you are, depending on what specifically you want, you can essentially just kind of write the problem that you want, and it more or less works. So that's an exciting thing, is really kind of like the flexibility of it. And then not only is it flexible, but it allows us to also look at problems with contact, which is really what we're interested in. So one of the problems that we looked at, for example, for contact, and we'll go into more details about why contact is an optimization problem in the next couple of slides, but we can formulate this problem, which is a parameter estimation problem, where essentially what we're trying to do is we have this observed data, right, of an interaction between an object and an environment, in that case, kind of a box sliding across a surface, and we might be interested in estimating parameter of that environment. So for example, the coefficient of friction between the box and the ground. So given that problem, that parameter estimation, right, so of minimizing that residual in the observed data, and then an embedded problem, which is essentially going to solve for the contact dynamics. That's something we can formulate as a Bilevel optimization problem, and then solve with our solver. And I think what's interesting is that the alternative to doing it the way that we have would be to kind of generate a much bigger nonlinear optimization problem that would introduce a lot of decision variable, because we'd have to essentially introduce decision variables for all the contact forces that are happening in each of the kind of data points that we have. And so because our method doesn't have to do that, we can scale better. And so all that to say that essentially for this problem of contact, our method is essentially scales better than kind of alternative methods. And it's specifically because it's using this bilevel optimization structure of the problem. Now, some section takeaways, if you have just kind of first part. So just in case that I lost some of you, and make sure that you just kind of get the main points, is that bilevel optimization problem or optimization problem nested into one another. And that's really kind of all there is about it. You either have a problem nested in the constraint or in the objective of another problem. Secondly, many solution methods for bilevel optimization essentially just embed then solvers into one another, right? You have embedded problems, and then what you're going to do is you're just going to embed solvers into one another. Kind of straightforward way of thinking about it. And then finally is a lot of kind of the problems that are currently being worked on that have this kind of bilevel nature can either be, in terms of their solution method, can either be classified as either rolling out the embedded solver, so differentiating through the solver process, or using something called fixed point based differentiation, which is more relying on KKT conditions in general and these sorts of things. And then our work finally specifically was to design kind of a very general purpose solver for these types of problem using automatic differentiation and combining it with a constraint nonlinear solver and showing that we could solve some interesting robotics problem with it. Now we're going to move on to part 2, which is a little bit more applied. So this was kind of very high level, very much kind of general purpose solution methods. We're going to go a little bit into specific application of robotics, which I'm personally excited about. So that's really kind of, the first part is really just really giving us the tools really that we need to then kind of tackle these interesting robotics problems. And the first one we're going to talk about is the one that I mentioned at this talk that I think really motivated our work into bilevel optimization and our research into bilevel optimization is the one of contact. So in terms of doing obstacle avoidance, a lot of people, I mean, most roboticists are familiar with trajectory optimization in one way or another as being kind of the workhorse of obstacle avoidance in many ways. I mean, at least one of them, for sure. So there's kind of an obvious question of like, okay, well, if you have contact in the environment, can you not just include contact dynamics inside a trajectory optimization problem? And there's definitely a rich history of doing that. And it's definitely something that people are still trying to this day to do as effectively as possible. But in general, once you formulate trajectory optimization problems and you put contact forces in them, the problems become slow and difficult to solve unless you kind of do a lot of massaging. So that's just kind of something to keep in mind. And now, so why is that? And I think that's really something that I think I want to convey today is why is once you put contact forces into trajectory optimization, why does it suddenly become significantly harder than your classical trajectory optimization problem? So we're going to look at the trajectory optimization problem in general, right? So usually it's some sort of minimization over some additive cost over the length of some trajectory, right? And we have some constraints, which are usually include our dynamics constraint, and then some initial and final state of the system. So we're interested in computing the control inputs to a robot. And then we're going to do that by solving this optimization problem. Now, when we're adding now the dynamic, once our dynamics involve contact forces, we can kind of break up the dynamics constraint into kind of 3 groups. The first one is we're going to have our typical rigid body dynamics constraint, which are the ones that are well understood and that we can solve fairly efficiently. But the fact that we've added contact forces now adds 2 more classes of constraint. One of them first is going to be the normal forces constraint, and the one is going to be friction cone constraint. The kind of typical way of then of having this constraint is that we're going to have to essentially introduce new decision variables. So some of them are going to be modeling the normal force being applied by the system against the environment, for example, and also kind of the friction force that also being applied between the system and the environment. So we're going to kind of have these 3 classes of constraint now: our rigid body dynamics, which is like most trajectory optimization problem, our normal force constraints, and our friction cone constraints. And this is really where the difficulty comes in, is that these 2 new classes of constraints, the friction constraint and the normal constraint, have this specific form, which is complementarity constraints. And essentially it takes this form. So if you have, for example, 2 variables x and y, x times y must equal 0, and both x and y have to be greater than 0. So that's just a kind of a general form of a complementary constraint. And the thing that really, there's two key things here to remember, is that first, complementarity constraints are very difficult to handle for nonlinear optimization solvers. So that's kind of just in general, if you just, they're kind of ill-behaved in general, they're very non-smooth. So as soon as you kind of throw them to nonlinear optimization solvers, the solver usually struggles a lot. So that's where it comes from. The second is like, well, okay, well, could we just avoid them? Well, they're sort of, the problem is that they're sort of, they're fundamental essentially to this problem. And to appreciate that, I'll describe a little bit how you can understand these complementary constraints. So in the context of these two variables, right, the way you can think of normal force is the complementarity constraint that relates to normal force. You can think of one variable being the distance between, for example, the foot and the ground, right? So let's say you have the foot pushing on the ground, like we have on this little picture here. And then we have the other variable would be the force, the force, and then the other one is, it's the distance between the foot and the ground. So you have these two variables. One of them is the force, and another one is the distance. And you can just think of how contact works in general. One of these has essentially to be 0 at all time. So either your foot is not touching to the ground, in which case the distance is non-zero, and then the force between your foot and the ground has to be 0, or the other way around, right? Or they're touching, essentially the foot is touching the ground, and then the normal force has to be, or can be non-zero. So it's really is unfortunately kind of fundamental to the way the physics of that problems work, is that you get these kind of complementarity constraint. So there's no really, I mean, there's ways around it, but you're kind of you're gonna have to essentially approximate the dynamics if you want to avoid them. Now, kind of our main insight is that, which we use as insight actually from kind of previous work, but not necessarily in this context specifically, is that essentially these friction constraint, these complementarity constraint, can also be written as optimality condition of a quadratic program. And if you're curious about kind of where that comes from, comes from the principle of maximum dissipation. So if you write your dynamics of contact and you use the principle of maximum dissipation, you'll get a quadratic program, and then the optimality conditions of that are going to be the complementarity friction constraints. The only thing you have to remember here is that essentially our friction constraints are the optimality condition of a quadratic program. And so that kind of inspired us to come up with this method where essentially instead of doing the classical way of including contact forces into trajectory optimization by putting complementarity constraints in, what we're doing is we're putting the QP corresponding, the quadratic program corresponding to those constraints directly into the problem. And so now we have, instead of having a nonlinear program with complementarity constraints, we have a bilevel optimization program. And so we have, for example, our rigid body dynamics. And in this example, we're only doing friction cone because we found that this is actually where most of the benefit comes from. And so we have our normal constraints, which we've kept as complementarity constraints. And then we have our friction lower problem, which is a quadratic program. And then we have, obviously, our initial and final conditions. And really kind of the key aspect here is what we're going to do to solve this problem, this bilevel optimization problem, is we're going to use two state-of-the-art solvers. So we're going to use a state-of-the-art nonlinear optimization solver to solve the upper problem. And then we're going to take a state-of-the-art solver, quadratic program solver, to solve the embedded problem. And we're going to combine them. So instead of asking kind of the nonlinear solver to do all the work and have to handle these nasty complementarity constraints, we're going to essentially get a QP solver to just solve these embedded problems, and then we're going to use the nonlinear solver to solve kind of the resulting bilevel problem. And so again, just kind of a summary, and then the way that we're going to get the gradient to kind of tie back to the solution methods I discussed is going to be kind of the first way of getting the gradient that I mentioned, which is through some sensitivity analysis. And then we're going to use, again, a state-of-the-art QP solver to solve the embedded problem. And so kind of applying that to kind of some benchmark problems, what we notice is that we actually can cut the runtime of these methods by about a half, which is not negligible. Obviously not changing by huge orders of magnitude, but still not negligible. And I think mostly for the second fact, so this is a second problem where we're also seeing that we're about cutting the runtime in half. But I think the important point to realize here is that we're making the runtime of these algorithms faster, but we're not approximating the dynamics. So the two problems that we're solving, if you look at, for example, the solution of this problem, which is just a box sliding across the ground, you can see that the solutions are effectively identical. And it really comes from the fact that our formulation is mathematically equivalent to the complementarity problem. So we had this huge, nasty, nonlinear program with complementarity constraint initially, and we formulated this Bilevel optimization problem that is mathematically equivalent, that makes no approximation, really, no additional approximation on any of kind of the contact physics, and we can get some computational gains out of it. And I think that really contrasts it with sort of some other ways of making contact easier. For example, Mujoko will smooth the contacts, right? So you'll end up with weird contact dynamics where you can have contact forces at the distance, where that complementarity behavior that I explained, where the foot has to be in contact with the ground in order for you to get a force, isn't necessarily enforced super strictly. So we think that's pretty exciting. And obviously, that's also we're also excited about kind of the type of hard problems that we can handle with this. And so this work was published a little while back, but we're excited to kind of try new, harder problem now that has just been invited to IGR for an extended publication. So now we'll move on to kind of our second application, which is going to be simple, efficient value learning. So kind of going back to our trajectory optimization, right, problem that we had initially, where we're trying to compute this control for a robot by solving this optimization problem. So the way that we actually made our contact problem easier, or just our trajectory optimization problem easier in general, whether it's contact related or not, is essentially we looked at these constraints, which are along the entire trajectory, right? And we made the constraint easier. So we took one of the dynamics constraint, and we made it easier for the solver to handle. We're going to look at sort of a different way now of making that problem easier so that it can be solved more efficiently and get us kind of higher quality solutions. We're not going to make the constraint easier, but we're going to have fewer constraints essentially in our problem. And I'll explain how we can go about that. So that's kind of the flip side, right, of making this problem easier. So if we start with our trajectory optimization problem, the context in which we're going to be solving that trajectory optimization problem is going to be in model predictive control. So imagine that you have, for example, a robot trying to accomplish a task. In that case, for example, a glider trying to perch on a little perch, essentially at the end of a runway, and it's trying to compute essentially a trajectory from now until kind of the perching time, right? So you'll have this problem that will kind of formulate it as such, where you'll have some additive cost along the entire trajectory, right? So each transition that it's planning all the way until the moment it perches with the perch is going to be added to the kind of total cost of our problem. And then you're also going to have constraints that are going to link kind of each one of our transition along that trajectory, right? What we're going to propose to do is we're going to use something called limited lookahead MPC. So instead of computing the entire trajectory all the way to kind of the final moment of our trajectory, we're going to shrink our trajectory. We're only going to compute up to a little bit of time into the future. And obviously, now that we've kind of changed our problem, we've literally just shortened the horizon over which we're computing our control actions. We're not solving the same problem anymore, right? Like we're not taking into account the perch at the end of the runway anymore. We're only taking kind of a short horizon into account. But the way that we're going to do this is we're going to introduce essentially a surrogate cost function, right? So initially, our full problem had kind of all this additive cost all the way until the end. But in this case, we're only going to have a few of those terms. But then at the end of our trajectory, we're going to evaluate kind of a special function that's going to essentially make up for the fact that we've truncated our solution. And this is known as limited lookahead MPC, and it's kind of a well-understood method. And if you're familiar with, for example, AlphaGo, it's kind of a flavor of it. And this is what we're going to employ here. Obviously, the big question, right, is how you come up with this surrogate cost. So it seems kind of very trivial to just shrink your horizon and then add a surrogate cost, but where does that come from? That's really the hard part and kind of the crux of that problem. I do want to point out kind of why we want to approach this problem that way, why we think this might be the way kind of forward in terms of doing these trajectory optimization, solving this trajectory optimization problem as fast as possible. That if we looked at the original problem was slow to solve. It takes a long time, but it's easy to adapt online. So we have, because you're planning your entire trajectory all the way to kind of the final time, you can, if there's new obstacles, for example, that come on the way along the trajectory, you can quickly adapt to it. You can change the trajectory easily and then get what you want. There's obviously a popular way of kind of doing that in a very computationally efficient way is to distill this into a policy, right? So directly kind of if you just have a policy that is just in closed form, then what you will have is you'll just have a function that online instead you'll just evaluate for a given state and it will give you the control actions to do, right? So some popular ways of doing it is you'll take kind of your original problem and then you'll do some learning, for example, or any method, there's plenty of methods, and then you'll synthesize this closed loop function that online you can just evaluate and then it tells you what to do. The problem with that is that it can be difficult online. There are ways, but it's not straightforward to necessarily adapt your policy online. So everything that you've done kind of before, in the way you've synthesized your policy, now you have a plan, you have a way of kind of interacting with the world that is sort of fixed, and it's kind of hard to adapt if there's, for example, new obstacles or you're in a new environment. Limited lookahead and PC is a little bit kind of in between those two. So because you have a shorter horizon, it's a little faster than kind of solving your original problem. But you do have that horizon over which you can adapt the problem, right? So if within that horizon, there's new obstacles or there's something that happens, you can adapt your control actions accordingly. So it's a compromise. This is kind of how I would explain it. So now going back to kind of how we're going to make this happen. So again, the difficult part is to learn this value function, right? This value function approximation, this surrogate cost that we will put into our optimization problem in order to shrink the horizon over which we're computing it. So what we're gonna do specifically for this problem is we're gonna essentially use a neural network to parameterize that surrogate cost. So we're gonna propose to learn our value function using a neural network. The one of the key observation to make here is that if we solve our full horizon trajectory optimization, the original big problem, all the way to the purge, and we look at the objective value of that problem, this is actually the value function that we need. So if you solve the original problem, you get that value function. And now what we need to do is to be able to kind of come up with an approximation of that value. And therefore that observation leads to kind of a pretty obvious supervised learning algorithms, which is, supervised learning based algorithm, which has been used before, but we're proposing to leverage here and leverage it here as well. And essentially what it entails is to offline, so before purging, as we're kind of just designing the control system, we're going to sample a bunch of initial state for a system. And then we're going to solve the full horizon trajectory optimization for all these initial state, right? And next, we're going to take all these trajectory optimization solutions, and we're going to use supervised learning to learn an approximate value functions using the result of those trajectory optimization. And then we're essentially going to repeat that process over and over again until we end up with a good surrogate cost for limited lookahead and PC. So that sounds great in practice. That sounds great in theory, but in practice, it's a little different because there's a bottleneck that gets created, right, with an approach like this, especially if you kind of look at problems that are difficult to solve, which, for example, problems with contact would be one of them. So the problem is that not only are we generating now samples offline, but we now have to solve a trajectory optimization problem for each one of these samples that we're generating. And so even if it's something we can do offline before we actually use the controller, it's still something that's fairly difficult to do and takes a while. And so we're gonna propose a different way of doing that. So the typical way would be, right, like I explained, we're gonna take our state space and we're gonna just sample a bunch of initial states over which we're gonna compute a trajectory optimization on. Instead, what we're proposing to do is we're gonna sample our state space over fewer samples. We're only gonna generate a subset of the samples we would normally generate, sorry. And then what we're gonna do is we're gonna generate the remaining number of our samples by essentially making them by making the first batch of samples slightly more adversarial. So what I mean by that is we're going to take our first samples and we're going to move them in a direction where approximation error, so the error between our current estimate of the value function and the true value function, is the highest, right? So that's something we can do in many ways. You could just take kind of a gradient step in the direction of that gradient, right? In the direction of that biggest error. Or something we can do kind of over multiple steps using something like Atom or using kind of a second order method. We'll take a couple of steps to kind of regions where that error is largest. So that sounds simple, right? Instead of generating a whole bunch of random samples, we're going to generate fewer random samples. And then we're going to take these samples and generate more samples, but they're going to be kind of in the right direction, in the direction where our approximation is poor. And it essentially gives you an algorithm, which we call Seagull for simple, efficient, adversarially adversarially guided learning of value function, which essentially just adds a step, right? So instead of randomly sampling initial states, we're going to randomly sample a subset of those, and then we're going to generate the rest adversarially. So it sounds simple, but there's a complication. So if you look at generating those samples, those kind of additional adversarial samples, so moving our samples into a direction where the fit is worse, you can essentially think of it as us solving this maximization problem, right? We're finding initial states where the value function and the approximated value functions have the biggest mismatch. So that's kind of the problem that we're solving when we're generating samples. But if you kind of expand that problem out, what you quickly find is that you actually have a max-min problem, right? So your adversarial sample generation has this nested optimization problem structure. And so by now you should kind of recognize this is a Bilevel optimization problem, kind of unsurprisingly, which complicates things a fair amount, but also is an opportunity in our case. So again, we're using this adversarial sampling scheme to generate states over which we'll compute our value function. But in our case, the adversarial sampling doesn't have kind of this straightforward structure. Our adversarial sampling, adversarial sampling optimization, adversarial sampling is itself a Bilevel optimization problem. And so the way we're going to do this is using kind of an off-the-shelf nonlinear solver to solve the kind of the lower problem. And then the way that we're going to differentiate is to use just kind of sensitivity-based analysis. But in our case, we're also going to use a special property, which I'm not going to go into too much details, but essentially this sensitivity, this fixed point-based differentiation that I mentioned earlier, for that particular problem takes a special form, which is kind of very computationally efficient. And for that reason, it makes our whole problem, our whole approach worthwhile. And I'm happy to go into more details, but for a question of times, we're going to go through that quickly. But all that to say that the specific nature of this Bilevel optimization problem makes this essentially kind of still a computationally attractive method in order to kind of generate our samples. And so we'll apply this to different systems. So for example, here we have the Acrobat on the left, as well as the perching glider that I described earlier on the right, where we have a kind of a glider being launched at an initial state and trying to perch on a perch kind of down a runway. And what I'm showing here is the validation loss over test samples. And sort of in blue here, you see that kind of our adversarially trained method essentially gives you a better, kind of an improved generalization, so a lower error on your validation set during training kind of earlier. So training over adversarial samples for the same number of samples essentially gives you kind of better performance in terms of test loss. And now this improved kind of fit in your value function, this improved fit in your surrogate cost also leads to obviously an improvement in control down the line. So if you take those surrogate costs and you formulate the limited lookahead MPC problem with them, and then you run out these controllers, and then you observe kind of the cost that they accrue when they're being rolled out, and you plot those. This is the kind of the plots that you get that shows that, for example, the ones that was using the random samples is after 50 samples is still kind of doesn't have a very good performance. So the Acrobat still cannot essentially stabilize for a wide range of initial state. But if you've trained over adversarial samples, that's not the case. You can have a fairly significant region of attraction, essentially over which you can stabilize the Acrobat. And same for the glider. It's a little bit hard to plot the Acrobat, but for the glider, here you can kind of visualize this trajectory also kind of in space and just see kind of the trajectory that they do. And so you can see kind of in blue here, those are the ones that we've trained adversarially. And you can see that even after a few samples, because your samples are chosen carefully using this Bilevel optimization problem, you can kind of already get the behavior that you want, even though the randomly trained is kind of far from being close to a good enough approximation of your value function. So that's neat for kind of these simple problems, and that's actually a result that's already been published. It's been accepted actually a couple of weeks ago, but now we're trying to kind of push the limit of what we can do with these types of methods. Specifically, we want to see if we can run these things online, right? If there's a way of kind of the whole framework, not just the adversarial training, which now we know is beneficial in many ways, whether kind of this whole framework of adversarially training a value function and then using it in this limited lookahead MPC method is something that's tractable and can solve problems. So we interesting problems online. So we designed this kind of simple experiment that is simple, but still pretty challenging because of how fast everything has to happen, where we have the Panda robot, so a robot actually right behind me right now, trying to catch a ball that's being thrown at it. So it sounds super simple, but the problem is actually fairly difficult in the sense that the timing of everything has to happen very quickly. And that's really something that I wanted to make sure that we're kind of challenging ourselves on that front and making sure that we're getting those methods to work in the right kind of frequency, in the right order of magnitude. And so to give you a sense, the time between the sensing of the ball, and the time that the ball is being catched is, about like half a second. So 500 milliseconds is the time that you have to plan and to do kind of the entire trajectory. So it's very, very fast. And so here we've ported the controller to hardware. And these are very early results. I don't want to kind of mislead anyone. This is definitely still not working at kind of the level of robustness that really we want for this result, but it is giving some pretty promising kind of first results. I'm just going to show a couple of those right now. So I'm out of the frame here, throwing the ball essentially, and then I showed one failure just to make sure that it's conveyed that this works a lot of times. Also, it doesn't work a lot of other times. But the important thing here is that our whole framework can be made to run real time, I think. And I think this is a demonstration that it can be, as long as you kind of leverage the right tricks, and then you, among other things, parallelize everything on GPUs, and then use other tricks that I can talk about in greater details as well. I'm not sure that the video was going to show well on Zoom, so I also have some stills from it here. This is about half a second of video, where I've colored the ball essentially in red, and shows that this is in that half second, essentially the ball is approaching very quickly the arm, and then we're asking an extremely dynamic maneuver from the Panda, which for anyone who's worked with the Panda knows that it's actually quite difficult to achieve. The Panda has all sorts of safety triggers that I had to remove essentially to make sure that even this would run. So this is how challenging this task is, and we're getting some pretty, I think, impressive and kind of promising result on that front. So we're pretty excited about that. So I'm going to talk about our last application of bilevel optimization to problems in robotics. And so we'll get going. And so I'm going to start by essentially bringing us back to the beginning of the talk, where I mentioned sauce programming, right? So initially I was talking about how progress in numerical optimization was really drove a lot of progress in control over the last couple of years. And I used sum of squares programming as kind of an example of that, right? So you kind of being a little bit more precise as to how sum of squares programming enable control, you will uncover that essentially it's enabling this by enabling us to synthesize something called barrier and Lyapunov functions. And I'm going to details what that is, but this is kind of how it really sum of squares programming enable all these control applications, is by enabling us to synthesize certificates known as barrier and Lyapunov functions. And so there's a natural question, right? Now that I've explored all this bilevel ideas, is there really kind of a parallel to that with bilevel optimization? So SAS allowed us to kind of generate these certificates. Can bilevel optimization do something similar, analogous? And obviously, as you might expect, since I'll talk about it, the answer is yes. But going into a little bit of detail, so I'll do a super quick review about what I mean by these certificates, these Lyapunov certificates. So many of you will know it, but just to make sure that we're all on the same page, given a dynamical system, essentially the existence of a Lyapunov function certifies that system is globally stable. So that means, and what we mean by that is that all trajectories converge to an equilibrium. So what's a Lyapunov function is essentially just a function of state that has the following kind of three properties, right? First, it has to be positive. Second, its time derivative has to be negative, and then it has to be radially unbounded. So you kind of just have to remember that if you have a dynamical system and you have a function that satisfies these three properties for that system, then you've proven it is stable. Now, intuitively, you know one probably already on top of your head for the damped pendulum. So if you take a damped pendulum, then the total energy of that system is actually a Lyapunov function for that. So if you compute the total energy and you kind of track it over time, that's a valid Lyapunov. Now, that's easy for the pendulum, but it's not as easy for kind of all class of systems. And there's certainly one class of system for which that's particularly challenging is piecewise linear systems. So finding Lyapunov functions for piecewise linear systems remains challenging at best. And that is true for kind of both continuous piecewise linear system and discrete time piecewise linear system. What are these systems? They're essentially just systems where we take the state space and we essentially partition it into different regions. And in each one of these regions, we're going to have a linear system, right? Linear dynamics. That's essentially what they are. And they're particularly important for a lot of different reasons. People use them to approximate general nonlinear system, but also been used to model system with contact. So again, a topic of particular interest for us. And so here's our approach, essentially to using kind of a Bilevel optimization approach to do this Lyapunov synthesis for piecewise linear system. So again, kind of going back at this pendulum idea, we had our system dynamics, that was the pendulum, and we had a Lyapunov function that, like I mentioned, was energy. Here, what we're suggesting is our system dynamics in this case is going to be general piecewise linear systems, and then our Lyapunov function is going to be parameterized as a neural network with value activation functions. So this is kind of our general approach. Why does that matter? Why is that a good idea? Well, it's a good idea for kind of two reasons. The first one is that given a candidate Lyapunov function as neural network with value activation, as well as piecewise linear dynamics, you can actually verify the Lyapunov condition by solving a mixed integer program. So the fact that you could kind of convert neural network into a mixed integer constraint was something that was established before, but specifically that you could check Lyapunov condition was something that we figured out. And that's appealing, right? So more precisely, if you take your candidate Lyapunov function, you can formulate this maximization problem that essentially proves the positivity of your Lyapunov function. If the result of that maximization is negative, sorry. And you can also formulate the second optimization problem, which is, again, another mixed integer program, that if the solution of that mixed integer program, again, is negative, then you've proven that second Lyapunov function. And the third one that I mentioned earlier is kind of satisfied by construction. So that's interesting, right? So if you give me a Lyapunov candidate as a neural network and piecewise linear dynamics, and you combine those, then I can verify that your candidate Lyapunov function is actually a valid Lyapunov as a mixed integer program. So that's one of the reasons of doing it this way. The second reason is that not only can you verify that Lyapunov conditions using a mixed integer program, but you can now synthesize the Lyapunov function by solving a Bilevel optimization problem. And it's pretty straightforward to formulate. Essentially what you will do is you will take that mixed integer program, the verification problem, and then you will use that as the embedded problem, and you'll formulate an upper level problem that will essentially be trying to find parameters of the neural network that satisfies those embedded constraints, right? So now you have the upper problem, which is trying to minimize the worst violation of the Lyapunov condition. And the way we're going to solve this more specifically, we're going to solve the upper problem using gradient descent on the neural network parameter, and we're going to the upper problem using gradient descent on the network parameter, and we're going to solve the lower problem using an off-the-shelf branching cut solver, Gurobi in our case. And so if you apply that to a couple of piecewise linear systems, you get some pretty cool results for both continuous time and discrete time systems. So you can see the Lyapunov function here. You can see with its level set kind of working out as expected, and then the violation, the two kind of results of the mixed integer program on the right, showing that what we found using kind of this Bilevel approach is indeed a valid Lyapunov function, proving the stability of our piecewise linear system. So that's kind of neat. I think it's kind of exciting. But I think we're most excited, and due to time constraint, I'm going to be very quick about this. But this framework can actually be extended to not only synthesize the Lyapunov function, but what you can do is, instead of looking at the dynamics of your system, you can now look at the closed loop dynamics of the system, right? So not only are you now synthesizing a Lyapunov function, but you can also synthesize the Lyapunov functions for a closed loop system. And not only can you do that, but you can also then make sure that your closed loop system has, for example, a neural network controller. And now you can learn both parameters of the Lyapunov function and of the controller. And so at the end, by applying our method to kind of that parameterization, you end up with not only a certificate of stability, but you also end up with its associated controller, which didn't necessarily exist before kind of you ran the algorithm. So that's kind of a very principal way using Bilevel optimization essentially to get like a certified feedback controller for a system. Okay, so some section takeaways just of that second part of the talk. So our work shows that many important problems in robotics have this kind of underlying bilevel optimization structure, right? So trajectory optimization with contact, adversarial learning of value function, and learning certificate for dynamical systems, as well as learning certifiably stable feedback controllers. Also, we show that leveraging modern solution methods to solve this problem explicitly as bilevel optimization has a lot of different benefit, including runtime and sampling efficiency, and all sorts of things that I've discussed in the talk. So all sorts of benefits that really makes this worthwhile to look at kind of these bilevel optimization methods. And with this, I will go into the conclusion. So just to recap our contribution, right, real quickly, we've shown a general purpose solution method for bilevel optimization problems. We've also shown how you could use a bilevel optimization solution for trajectory optimization through contact. We've shown that you can also do efficient value function learning with this bilevel optimization method. We've also shown how you can do Lyapunov synthesis and using, again, the similar class of method. And I hope I also convince you that using kind of this class of methods, you can kind of make a lot of progress on these contact-related problem and hopefully move us a little bit closer, at least making kind of a step forward away from Autonomy 1.0 and Autonomy 2.0, where hopefully we're going to be making contact as easily as we're today doing obstacle avoidance. And with this, I want to thank all my collaborators, especially highlighting the ones that have collaborated with me on the work that I've talked about here, and all the other ones that who I've done work with that unfortunately couldn't make it into this presentation, and also the organization that supported me, as well as my committee, Professor Pavone, Professor Bogue, Professor Manchester, Professor Kennedy, and Professor Krakowski. Thank you very much for agreeing to be here early in the morning on Friday. And obviously all of ASL for their incredible work during all my time here, and camaraderie, as well as obviously my family, starting with Lindsay, my wife, who's been there for all these years and has been incredible, as well as my family, Michel, Luce, Simon-Pierre, Marianne, Vanessa, and Maxime. And finally, a shout out to New York Pizza, who's provided an estimated $30,000 worth of pizza for the robotics seminar over the last 3 years. So special shout out to them. And with that, I will open for questions.